In this video, I'd like to share my commentary on the solutions that I posted to the homework number 6 test 2 review. These are the questions that showed up in Math Excel, and I've provided a document that shows my solutions with work shown. I've also added a few notes at the side of each problem, NC or CP, and those stand for no calculator or calculator permitted. So if you're worried about what type of questions you'll see on the calculator and no calculator portion of the test this week, here are some notes to help you recognize that. So in problems like 1 and 2, we're simply substituting values in for x in our function notation. And there really shouldn't be anything new here, just an opportunity for you to practice your algebra and simplifying some of your results. So for example, on number 1, we're substituting -7 into this equation. And anytime that I perform a substitution, I use a set of parentheses, and I place a number inside there, especially when the number is negative. That helps me understand the end result just a little bit more clearly. Now, since this is no calculator, I went ahead and did most of that math off to the side over here. But if calculator was permitted, then I would probably show this setup and then jump straight to the final answer. But since I didn't know what the answer would be, I had to break it down into pieces. Same thing happens when we substitute in a -x. We evaluate the function and simplify. In part 3, it may not be immediately obvious, but a negative sign in front of the function would literally be a negative sign in front of the function wrapped in a grouping symbol. And this negative symbol here does distribute into each of the 3 terms. We can simplify from there. Now, these two are good previews for our discussion on even versus odd symmetry. So understanding what f evaluated at the inverse of x should look like, the opposite of x should look like, and then the opposite of f of x, knowing what that should look like, would help us determine whether the function is even or odd. The last component is really a preview of calculus class, and in this case we substituted the binomial x plus h in place of x. So here again I'm using parentheses to indicate that substitution. I expanded the binomial squared, and I used a FOILing process to simplify that, and then I distributed the 4 in. We can do that because within a group of multiplication, within a group of numbers that are being multiplied, multiplication is commutative, so we can multiply them in any order. So I completed the square first and then distributed the 4 in, and I also distributed the 3 towards the end here and ended up with a large expression with lots of components. We talked briefly about this in class or in one of my videos. This is called the difference quotient, and my calculus students spend a lot of time talking about those at the beginning of their calculus class. Problem number 2 is done much the same way, so you can pause the video now if you'd like and see my substitution and follow my work habits. Moving on to number 3. This is another no calculator question, and there really shouldn't be any surprises as far as answering questions A through F on this. I just wanted to point out here that it's possible to see some alternative notation. When we're asking if a function is positive or negative, we're essentially asking if f of, in this case, -6 is greater than 0 or less than 0. Since f of -6 is positive, an appropriate way to write that using notation is like this: f of -6 is greater than 0. For part E, I'm reminding you that while Math Excel is looking for an answer like this, separated by commas only, it really is more appropriate to include the braces on either end. When we have a set of numbers or a set of solutions, we should capture that set with the braces. For part F and G, when we're talking about domain and range, especially when using interval notation, I think it's more appropriate to include the element symbol, x element, y element. So I would encourage you to get in the habit of doing that, especially since our test is going to be on paper this week. And then also on H and I, we are identifying X and Y intercepts. On Math Excel, they're okay with leaving your answers and separating them by commas, but the answers they're looking for are just numbers. Numbers like -12, -2, and 8. What I like to stress is that since x-intercepts and y-intercepts are coordinates, they are points, I would rather see the solutions written as a coordinate or as a point and separated by commas that way. The other thing worth noting too is that all x-intercepts occur when y is equal to 0, and all y-intercepts occur when x is 0. And as long as we're dealing with a function, a graph that passes the vertical line test, there can only be one y-intercept. There can't be any more than that. There might be an example where there are no y-intercepts, but there can never be more than one y-intercept. For J, again, I used the braces for set notation. And for K, well, it was just a single answer, so we don't necessarily need the set notation there. For number 4, I forgot that I didn't go back and complete this problem for this video, but we had one almost identical to it in our Unit 2, Part 2, Lesson 1 series. And if I'm not mistaken, I think it was in Video 2 or maybe Video 3 from that group. You can go back and look at it to see my approach on this problem. For number 5, again, we're looking at a calculator permitted question. So here's a function that describes the cost per passenger on a flight, and the cost per passenger is affected by the ground speed of that airplane. So if it's receiving any assistance or resistance on account of airspeed, on account of the wind speed as it's up in the air, pushing itself, that could affect the cost to operate the aircraft. Of course, if it's flying in a headwind, it's going to cost more to operate. If it's got a tailwind helping to push it along, it's going to cost less. So the first thing we need to do is graph this function, and that's pretty easy to do with the graphing calculator. What I wanted to point out here is that the instructions in Part A do specify our window. So we're being told to graph this with an x value from 0 to 1,000 and from y values 0 to 1,000. When you graph that function, any one of these 3 graphs might look like the correct one, but as long as you have the appropriate x and y axis, from 0 to 1,000 on the x-axis and 0 to 1,000 on the y-axis, even if your scales differ slightly because of the shape of the window, the overall shape of the graph should be this one here, where we reach a bottom and then we slowly increase. We don't reach a low point and rapidly increase, and we don't have this graph where it tends to decrease all the way across. Part B is the best match in this case. For Part B, we didn't address how to do this in class using the table functions. It just wasn't worth the effort to reteach that or to record a video on it. But I do think that you should be capable of building your own table manually as needed to answer these questions. And so Part B is literally just asking us to build a table that starts at 0 and has a delta or a change in our table values of 50 units. And this would allow us to essentially find the ground speed that minimizes the cost per passenger. So at time 0, if I used an x value of 0 and plugged it into the equation, I would get an undefined result. We can't have a ground speed of 0 and still fly the plane. If that plane had a ground speed of just 50 miles an hour, it must have been facing a pretty terrible headwind. Well, when we plug 50 into the equation, we ended up with $905 as a cost per passenger. And what I did is I just ended up building this table, and I continue adding to it in increments of 50 as indicated by the problem. And what I was looking for is when the function results, c of x, seemed to hit a low point. And they were decreasing all the way along. I ran out of room and moved on to the second row. And in the second row here, we saw that they were decreasing still, although they were decreasing pretty slowly. And then all of a sudden at 650, I hit a low point. And I know I hit a low point because we hit a minimum here. We hit a minimum here because we changed from a decreasing function to an increasing function. That's what indicates a minimum point. So I knew that the function was decreasing because the numbers were getting smaller. Then we switched to increasing because the results were getting larger. And when we switched from decreasing to increasing, I knew that we had reached a minimum point. So if the airplane could be flying at 650 miles per hour above the ground, even though it's only pushing itself 500 miles per hour, right? It's using its engines to fly at 500 miles an hour. It must be receiving a tailwind of 150 miles an hour, pushing it along, and thus reducing the cost to the passengers. For part 6, we switch back to a no calculator question. This is, again, using our slope formula to find a slope between 2 points. The slope formula is this one, m equals y2 minus y1 over x2 minus x1. And the reason why I included this is so that you can have the practice. And what I was trying to point out here is that it doesn't matter the order in which you subtract, whether you take 8 minus 2 for your y values and then 6 minus 9 for x, or the other direction, 2 minus 8 and 9 minus 6, the end result will be the same. The only way that you can get this mixed up is if you don't keep the x and y coordinates together. For example, the y coordinate 2 must be paired with 9, the y coordinate 8 must be paired with the x coordinate 6, because that's how they were specified in the given information. Moving on to number 7. This time we're being asked to write an equation in point-slope form. Linear equations take on many different forms, whether it's standard form, point-slope, slope-intercept, etc. This is the format for point-slope form, keeping in mind that y1 represents the y-coordinate from the given point, x1 represents the x-coordinate from the given point, and m, of course, is the slope of the equation. So as long as you make your substitutions, you should be in pretty good shape. The instructions did say to simplify, so instead of leaving this as x minus a negative 9, it would be appropriate to report this as y minus 5 equals 4 times x plus 9. For question number 8, this is a vocabulary question, verifying that you understand the definition for even versus odd. Even functions take on this form here, where we insert a negative x, simplify the result, and end up with the original function again. If we insert a negative x into the function and simplify and get the opposite of the original function, then we're dealing with an odd function, or a function with odd symmetry. For question 9 and 10, since the instructions said to determine algebraically, then that would imply that we're talking about a no calculator question. We addressed these in class, and the work that I've shown here simply substitutes a negative x value in place of x in the original function, and we would simplify. In both of these cases, the simplified result ended up being the same as the original function. Therefore, we were dealing with an even function. For number 11 and number 12, I just switched the wording around for this handout to say graphically. If the instructions say to determine graphically whether the function is even, odd, or neither, then we would simply look at the graph itself on our graphing calculator. And if the symmetry isn't present, either reflectional or rotational symmetry, then we mark this as neither. This doesn't have the reflectional symmetry across the y-axis, and it does not have the rotational symmetry about the origin either. So we would say that this function is neither. If you were to try to do this algebraically, then I've kind of got that started over here on the top right, but we haven't really discussed how to simplify this issue here when you substitute a negative variable inside of an absolute value function. And it can be kind of tricky if you're not careful. You may have seen this in the past, and you may be comfortable trying this on your own, and if that's the case, then go for it. For number 12, it's the same sort of thing. Since this is a graphic example, we would use a calculator to solve it. And on the calculator, I wouldn't do any arithmetic with it. I would literally use the calculator to graph the function and then decide whether that function exhibits our appropriate symmetry. In this case, it does exhibit the rotational symmetry of 180 degrees about the origin, so we would call it an odd function. In numbers 13 and I believe 14, and 15 too for that matter, all three of these are talking about average rates of change, and average rates of change are just another name for slope. So we're just asking you to calculate the slope of 2 points on this function. Keep in mind that the instructions will only give you x values, and with those x values you must compute the y values using the function that's provided. Once you obtain the two y values and you compare those to the two x values that are given, you should have no trouble computing your average rate of change, or slope, between those 2 points. For number 16, we're using the graph. So this is a no calculator question because the graph is provided. We're using the graph to answer questions about the domain and range, as well as intervals of increasing versus decreasing. And so this question is asking, is the function increasing on the interval from 3 to 5? And so from 3 up to 5, and those are parentheses, so we should really use open circles here. If you're thinking about the x-axis, there's the interval from 3 to 5, not including 3 and not including 5 on the x-axis. That correlates to this section of the graph. We always read from left to right when we're trying to describe increasing versus decreasing. And as we run from left to right, you can see that this function is dropping down. So we would say that it is decreasing, not increasing. For number 17, it's asking, is this function increasing on the interval from -2 to 3? So I marked the interval from -2 to 3, but you'll notice that it decreases for some of that time and then increases. So while there is some points of increasing value, it's not strictly or only increasing on that interval. So we have to answer no in this question. I did add some additional points here just to remind you. As we switch from an increasing function to a decreasing function, if we switch from increasing to decreasing, that implies that we've located a maximum point, either a local maximum or a global maximum, absolute maximum. Anytime we switch from increasing to decreasing, we reach a high point. The opposite is true if we switch from decreasing to increasing. A switch from a decreasing function to an increasing function does imply that we've reached a minimum on the graph. And we have, in this case, 3 minimums and 2 maximums. The local minimums are identified as just simply maximum points or minimum points, but the term locally means that it's not the highest or the lowest point. And when we talk about the highest or the lowest point in a given function, we call that either the global maximum or minimum or the absolute maximum or minimum. So in this case, the absolute minimum occurred down here at the coordinate -8, -9, and the absolute or global maximum occurred here at -2, 9. For number 18, we're identifying the intervals on which f is increasing. This is particularly interesting because the problem did come out and state that you need to return your result in interval notation. Even though Math Excel is really only looking for this component, I do believe that the best answer would include the element notation. For number 19, same sort of thing. This time we're being asked if at x equals 1 there's a maximum, and I would answer yes, there's a maximum here because we're switching from an increasing function to a decreasing function. As long as we make that switch, then we know we've located the maximum. For number 20, this is kind of interesting because this appears to be some sort of sine or cosine function where the graph oscillates, but doesn't really increase beyond this wave as we move from left to right across the graph. So we're being asked if there is a local maximum. And again, a maximum occurs when we switch from an increasing function to a decreasing function. And that happened twice in this window. So the two locations where that happened were at -4 and at +12 on the x-axis. So we entered both of those results and separated them by a comma for Math Excel. The tricky part to remember here is that since there are two maxima, then we need to locate or identify two y coordinates to go with them. And even though the y coordinates are the same, they both have a y coordinate of 16, we do need to list them twice because there are two maximum points. For number 21, again, the graph is provided, so no calculator is needed, and I don't think there are any surprises with this question. Now, as we get into questions like 22, this is another example of the application problems. We've talked about these in class, and I've also included a few of them in a video as well. Rather than let this particular video get too long, I'm not going to talk about this particular problem specifically, but if this is one that's bothering you, please send me a message or bring it up in class this week before the test, and we'll go over it more. But this particular example is going to be a no calculator question since we're only asking for the area function when we're done. We're not actually going to evaluate it. For number 23, I called this a calculator permitted question, but really that's only calculator permitted because of part C. I could ask the questions A and B on a no calculator question, or on a no calculator test. But what was interesting here is that we've got this rectangle that's fit underneath the parabola, 1 minus x squared. And one thing to keep in mind is that while rectangles can be formed with any point along this curve, we want to avoid rectangles that are developed in this region. So if I had a point here, I don't necessarily want this particular rectangle in question. If I ended up having a point down here, I'm not particularly interested in this rectangle either. And that was specified in the instructions here. And so because of that, we're relegated to results that only exist in quadrant number 1. And for that reason, we asked about the domain of the area function. After we establish that area function, since we're stuck between here, the y-axis, and here, the point of intersection, it was worthwhile computing where that x-intercept occurs by setting y equal to 0 and solving for x. And so this function would strike the x-axis at an x value of 1, and so we're interested in all x values between 0 and 1 because that would keep our rectangle in this first quadrant. Using the graph on the calculator, and it came up like this, I was able to use the maximum function to locate this point. And I think 2 decimals is pretty good. If we need more than that and your calculator doesn't display it, I'd be happy to show you how you can adjust that either in class on Wednesday and Thursday when we practice, or on test day as well. I can show you how to fix that pretty quickly too. Question 24 was done in class already before, so I won't walk through it again. But again, A and B could probably be done without a calculator. This particular one is calculator permitted because of questions like C and D. We would graph each of those functions and find maximum points or minimum points if the answer is meaningful. We would find those maximum and minimum points using the calculator's graph. Now, 25. This one is definitely a challenge problem and not fair for me to ask on the test. I think it's a really good question that incorporates our understanding of geometry from last year or the year before when you last saw it, and function notation that we see this year. But in all honesty, the tricks that we had to use, or the the components of an equilateral triangle that we had to remember in order to make this efficient are not something that I would ask you to recall in this particular class. If I had given you, a significant amount of time to work on this with some reference material, then maybe, but as far as a test goes, it's just not that great. So I do have my work here. There's actually three sections to this problem, and I worked from one to the other and on. So if you'd like a further explanation from me on that, I can provide that to you. I just won't do that in this video. Problem number 26 is an example of that intersection problem that we covered in class. So again, I'm not going to talk through it, but after you've practiced this a few times, you can pick up on the shortcuts here. I was able to establish this distance formula without drawing a diagram, and then I was able to simplify that pretty easily in about 2 or 3 steps. The graph on the calculator was needed to answer part B, and that was really the only time that a calculator was needed. For numbers 27 through 30 in this problem set, keep in mind that I could ask these questions in which you respond in interval notation or set notation. And while that doesn't affect answers for A, B, and C when we're addressing a single value, it does affect how we would report our answers with an interval of solutions or a range of solutions. So I've included answers for D, E, and F in both interval notation in the blanks as well as set notation off to the right-hand side. Excuse me. Some instructors don't mind if set notation is reported this way with just the inequality symbols. In a sense, that's fine, but again, with our goal being thorough and operating at the college level, I think it would be more appropriate to include the full notation in which we include the braces as well as our additional notation. As we're reading this from left to right in interval notation, we're saying that the solution to this problem are all x values that are an element or that are in the interval from 25 to infinity, non-inclusive. And as we read this answer, we're talking about the solution being the set of x's such that x is greater than 25. So all x's so that x is greater than 25. That's going to be our solution set. I think that pretty much does it for this video, although in the last question, second to last question as well, I started changing some of the notes around. Again, this is just meant to remind you that we could have inequality symbols that include the equal sign, and that would affect our would affect our boundary notation. So if your Math Excel questions didn't vary all that much, for my example, 28 and 30 were just like 26 and 27. So since they didn't vary, I felt that it was important to at least consider what the equation or what the answers might look like if our boundary was slightly different. So I think I misspoke there, but I meant 27 and 28 were just like my 29 and 30. The questions were set up identically to one another with no differences in the boundary notation, but we should be able to handle that. So I know this was a long video. Hopefully you got something from it if you watched the whole thing. Even if you just fast forwarded to the parts that, that you found most useful, again, I hope that that becomes some additional help for you while prepping for your test on Friday. If you have further questions, please let me know. I'll see you in class Wednesday and Thursday, and then the test on Friday. Thanks for watching.